So tell me if you can see my slides.
I can see them fine on my computer.
Okay, so I will start. Today I'm going to talk about Vulkan. Sorry. Okay, Vulkan is a new generation API for graphics and compute. It is released in 2016 by Kronos Group. Vulkan is cross-platform. It is available on multiple operating systems such as Windows, Linux, Android, Mac OS, iOS, as well as some operating system running on game consoles like Nintendo Switch and the Steam machine. Vulkan is also cross-vendor. Over 140 members participate in the development of the Vulkan standard. These include many big companies such as NVIDIA, AMD, Intel, and Apple. So right now, Vulkan focus exclusively on C language binding, but there are many open source projects provide bindings for numerous programming languages such as C++, C#, Rust, JavaScript, and many others. And next, I'm going to talk about some highlights of Vulkan. So the first one is explicit control. The top reason that prompted the development of Vulkan is performance. To achieve this goal, Vulkan puts more work and responsibility into application compared to OpenGL. This includes memory allocation, thread management, synchronization between CPU and GPU. The point is, Vulkan gives you explicit control over graphics. That means your promise, you are going to tell Vulkan driver what you are going to do in sufficient detail. And in return, the Vulkan driver does exactly what you ask for, and it doesn't have to guess. While in OpenGL, drivers often defer work, defer work later and maybe move it to another thread, or even ignore your commands based on the guesses about your intent. So Vulkan is a low-level API with thin driver, and there is no driver magic in Vulkan. So, besides, the application usually has a better knowledge for holistic optimization, and we are happy that Vulkan gives the application more power to do it. The next highlight is command buffer. In Vulkan, graphics commands are like bind, draw, copy are sent to command buffers. And it is possible to have simultaneous command buffers. And each command buffer can be filled from a different thread. Meanwhile, command buffers can be flushed into queues only when needed. The Vulkan separates the time point of creation and submission of command buffers. And so you can prepare command buffers in multiple threads in advance before entering the render loop, and only submit your command buffers into queues when needed. This will gives you better frame rate since this will give you much better frame rate since you do less work in the main loop. The next one is error checking. I want to talk about the drawback of OpenGL's error checking strategy. In OpenGL, the driver has extensive runtime error checking, but many error comes from result from application, result from programming mistakes. Will only occur at during development, and they will always be fixed. The problem is in the release build of your application, this runtime error checking cannot be disabled. It must still work. So this increases the driver overhead and result in a waste of CPU cycles. What Vulkan does is that it doesn't require the driver to implement any runtime error checking. Instead, it provides layer system to you. Layers are layer libraries that can be inserted between the application and Vulkan API entry points. So your API calls will be dispatched to layers first and then the driver. The point is these layers are optional and you can disable it. Meanwhile, the Kronos group provides validation layers that can detect and report incorrect usage of the API. So the common strategy of error checking in Vulkan is enable the validation layers during development and disable it in the release version of your applications. And the next highlight I want to talk about is SpareV. Just like in OpenGL, we need to write our own shader programs. But the difference is in Vulkan, shader source files are half precompiled into intermediate form with external compiler. This intermediate form is called SpareV, known as a standard portable intermediate representation for Vulkan. And then the SpareV gets turned into fully compiled at runtime, as shown in the figure 4. It has many benefits to use SpareV. The first one is the software vendors do not need to ship their shader source with their softwares, and it makes sense that the software vendors don't want to expose their source code into public. The next is syntax errors can be detected at compile time. You don't need to recompile your entire software and write some extra code only for checking syntax errors in your shader programs. And software can launch faster because half of the compilation has already taken place. This is important because we care of performance in Vulkan. And SpareV allows for different shader languages as long as you have a compiler that compile you languages into SpareV. And right now, GLSL, the shader language used in OpenGL, and HLSL, the shader language used in DirectX, are supported well in Vulkan ecosystem. Here is the architecture of a Vulkan application. So we can your application is on the top, and instance is a set of it's a set of devices with certain properties, and you can have the same instance with different properties and call them different instances. The physical device is just the physical device. It is common for one computer have multiple graphics. For example, most gaming laptops have a high performance discrete graphics and another integrated graphics built into the processor. The logical device. The logical device is the interface to the physical device. And it is possible to have multiple logical devices with different properties and has different work to do. And then we have queues and command buffers point to queues. This is the architecture of your application if you want, but a more typical cases is we only use one instance, one physical device, one logical device. So Vulkan is a low-level API, and it gives you explicit control over graphics. So it has the flexibility to adapt to whatever you are rendering for and whatever you are computing for. And next, I will show you some examples about Vulkan C API. At the very beginning, I want to clarify that I didn't do any error handling in the following examples because I want to simplify the code and I want to emphasize the patterns used in Vulkan. So the first example is querying available physical devices to in a Vulkan instance. So we use the function called vk enumerate physical devices. It has three parameters. The first one is a handle to Vulkan instance. The second one is a pointer to an integer related to the number of physical devices we are going to query. We are going to query, and the third parameter is either null or a pointer to an array of vk physical devices device handles. So notice that we call this function twice, and in the first call we left the third argument to null pointer. In this case, where the Vulkan knows we only cares the number of the physical devices. So in this call, the Vulkan will return the device count. Will return the number of physical devices into this parameter, and then after we get the number of the physical devices, we can create an array that have enough space to hold the physical devices. I use std vector here to be convenient. So in the second call, we passed the pointer to the array as the third argument of this function. And this time, since Vulkan knows the third parameter is not a null pointer, and Vulkan will overwrite the physical devices to the array we passed. And this is the way, this is Vulkan's way of querying things, and this pattern is widely used in Vulkan. Besides, we need to query a lot of things such as available extensions and available layers. The next example I want to show you is how to pass information in Vulkan. We know that in Vulkan, we know that in Vulkan we have to we have to we know that in Vulkan there are so much information we have to fill, and it is crazy for Vulkan to create a function with 20 parameters. So instead, Vulkan provides some structs like the blue one and white one here, and what you need to do is to fill these structs and then pass the address of the struct into the function. Just like what we did in line 11 and line 24, we passed the address of the struct instead of using a function with 20 parameters. Since we all use C++, so I want to introduce C++ bindings briefly. So Vulkan HPP is a third-party open source project maintained by NVIDIA. It provides header-only C++ bindings for Vulkan C API, and it adds features like type safety for enums and standard template library container supports and exceptions. So in the listing 3, this listing 3 shows the example of enumerating physical devices with Vulkan HPP. The code above the line is as same as the previous example, and the code under the line is the enumerating using Vulkan HPP. So we can see we no longer need to call this function twice, and the instance object has a member function, and this member function returns the available physical devices within a std vector directly. So 4 or 5 lines of code get turned into 1 line of code. It's much better. And the next example is how we create struct using Vulkan HPP. When using the Vulkan C API, there are some issues when filling a struct, and these issues cannot be detected at compile time. For example, the initialization of struct elements and the use of incorrect enums, C enums. So what Vulkan HPP does is it introduces constructors for all structs. So the first element for all structs, S type, is automatically filled with the correct value, and all other values is set to 0 by default. And we use C++ scoped enums instead of the C enums. This brings us a type safety. And if your compiler supports C++ 20 designate initializers, so you initialize your creation of construct using Vulkan HPP will look like in line 13 to 16. As we can see, it is much better than the above code. And basically, that's all of my presentation. Thank you. Any questions?
If no one else has any questions, I have a few that I can ask. I wanted to ask with respect to the validation layer that you were describing in terms of the overall architecture for Vulkan. I'm just sort of curious, like I'm not I don't know very much about Vulkan at all, really. Basically, I just know what you've told me before in other talks that we've had or discussions that we've had. But I'm wondering, is it basically the mechanism by which you get from the application into the driver is you're calling through function pointers, and then is the basic idea behind validation layers is that you would kind of plug in a different set of function pointers that would then indirect you into some other code that would do checking, and then it would in turn call the pointers that function pointers that take you into the driver. Is that sort of how it works? So the layers like add an extra level of interaction.
The function calls, the function is called to Vulkan C API will dispatch to the layers first, and then dispatch to the entry points in driver. So basically, these layers are hooked into the driver. It can be disabled anytime as you want. So if you disable it, there won't be any overhead.
Okay, I'm just wondering, like if you're not using the layer, like when the application invokes some functionality in Vulkan, I guess are all function calls like through some kind of function pointer, and then the way that you would inject the validation layer is that secretly behind the application's back, the pointers would be replaced with pointers that take you into the validation layer, and then the validation layer would then in turn call the driver. Is that sort of, I'm just trying to understand the mechanism by which you at runtime can kind of plug in the validation layers or not plug them in. I guess that would sort of imply that all the calls are being made through function pointers that can be like substituted with different values that would take you into the validation layer. Or if you don't know, that's fine. I'm just curious.
I don't know too much details about the layers, but actually there's a loader in Vulkan that actually this one should be loader, but I didn't introduce loader here, so I replaced with application, but the meaning doesn't change. And if there's no layers, I think that the loader will directly dispatch you API calls to the driver. And if you have layers, well, I don't know. Maybe it will make some link between the layers and entry points and the Vulkan API entry points, and so the API calls will first send to the layers and then send to the drivers by layers. So.
Okay, so it sounds like maybe things are more complicated than I thought they might be, which would probably lead to more efficient, like a more efficient like system.
Yeah.
Does anyone else have any questions? Or I have a few more I can ask, but I'd like to give students the opportunity to ask questions. By the way, it's always a good experience for students to ask questions as well, because sometimes you can learn stuff beyond just the answer to the question that you're asking when you ask a question. Maybe I'll ask another one.
Okay.
So you mentioned that there is sort of an intermediate representation, the so-called SpareV, that's used by Vulkan. And you said there's at least two different kind of popular source languages that are used to translate into it, like GLSL and then
GLSL, yes,
DirectX or something like that. I'm just wondering which is most popular. Is like GLSL used the most frequently, or is it a fairly even split between that and DirectX?
It's GLSL. It is much popular than other shader languages, since the Vulkan is managed by Kronos Group, and the OpenGL is also their project. So the Vulkan naturally uses GLSL as the first choice. And nowadays there are many new shader languages. So you can even use C++ as a shader languages. It has a compiler that can compile C++ code into SpareV.
But can it handle like fairly general code? Like, so SpareV is a fairly general intermediate representation. It's not something like VM object code or something, or not.
Yes,
something
it's pretty
like
general, and it is also used in OpenCL. And actually, it is derived from OpenCL. The Spare is first used in OpenCL that can turn OpenCL code to other platforms.
Okay, that would seem very powerful. You could like run like a lot of arbitrary code on GPUs, I guess.
Yes, you can use LLVM to create your own languages that can compile to SpareV.
Well, actually, that leads to another question. Do you know if GC, well, obviously Clang supports SpareV from what you said. Do you know if GCC supports it by any chance? Or is it just Clang?
I don't know.
Okay. I guess you've probably been using it with Clang then, probably, in what you've been writing? Or what have you been using for SpareV like generation for the applications you've been working on, or have you not been writing applications?
There are several open source projects that turns GLSL into SpareV, and the most popular one I think is called GLS long, I guess. GSL. I can't remember the exact name of that compiler, but it is the most popular one. And it is I think it is built based on LLVM, built on Cloud.
Okay. And maybe one last question. I think this was on slide 11. You were talking about the C++ bindings or something, and you mentioned something to the effect that like you made mention of exceptions. So I was just kind of curious, like in the C++.
Oh yes.
Vulkan, because my understanding is like I'm not by any means an expert on game writing, but from what I've heard, like one of the big fiascos in C++ language is exceptions, because they kind of violate one of the rules that if you don't use them, it doesn't really cost you stuff at runtime, but they do incur some costs. So I know some games developers, or at least my understanding is they just don't use exceptions. Like you're not allowed to use them because they're not willing to incur the cost of using them. So they'll basically disable exceptions in the compiler. So I was just kind of curious here when you mentioned that they're making some kind of use of exceptions, I guess, in the C++ bindings. Like, to what extent do they use exceptions? Because I thought that maybe they wouldn't want to use them, because my understanding is in a lot of games they actually build, like in the C++ compiler options, they will typically turn off exceptions, so you can't use them at all. Does that make sense?
Yes, it makes sense. Actually, the exceptions is optional in Vulkan HPP, and you can fully disable it and just use the return value for error checking, just like the C API. So actually, this function, all Vulkan C API has a return value that indicates you whether the whether the function operate successfully or not. And if you enable exceptions, if something goes wrong, this function will throw an exception. But if you disable the disable exception, this function will just return the same thing that the C API will return.
Okay, that makes sense. So yes, they're covering sort of both use cases. If you don't want to use exceptions, that's fine. You can use the library with them turned off. But if you would like to use them, you can still use them.
Yes.
Okay, that's all the questions I have. Thank you. Your answers have been quite helpful.
Okay, thank you. So I'm going to stop sharing my screen.
Okay, I'll stop the recording as well.